Welcome. It is Friday, August 21st, and today we are going to continue with our investigations of inverse functions, and we're going to learn how do you determine if a function does have an inverse, and then algebraically how to go ahead and calculate that. So let's get started. All right, so when we're finding an inverse, okay, all we're doing, remember, an inverse reverses what a function does. So if you look at this function, it takes an input, it multiplies it by 3, and then it adds 5 to it. Okay, so if we had a little animation here, our x goes into this machine, and it comes out 3x because it got multiplied by 3. Okay, then it's going to have 5 added to it, and it comes out to be 3x plus 5. Now, the inverse of this would undo or reverse what happened to that variable. So if you remember, the variable got multiplied by 3, then it got 5 added to it. So if we were going to reverse that, the way we would do it is, oh geez, the Death Star. Jeez, oh flip. Okay. We're coming up on the Death Star, guys. To reverse this, we would subtract 5 and then divide by 3, and that would give us the revert. It would undo what was done to the function here. All right, so this is what that would look like. Okay, we're going to now start with x, but we're going to put it into it's going to go backwards through the machine in reverse order. So in it goes in the out, basically, and we're going to subtract 5 from it. Okay, then instead of multiplying it by 3, because it's going in a reverse order, we're going to divide it by 3, and that is our inverse. These two things undo each other. If we composed them, what we did yesterday, then the result would be the identity function x. All right, you can tell if a function has an inverse if it passes the horizontal line test. If a horizontal line crosses the graph of a function more than once, there is no inverse function. That means it fails the horizontal line test. Okay, so for example, if the question's asking, does this graph have an inverse? Well, if we have a pencil, think of a pencil as a horizontal line, it touches this graph in more than one place. Touches it right there, touches it right there. So this graph would not have an inverse. It fails the horizontal line test. Okay, because a pencil crosses it more than once. Now what that means is this is not a one-to-one function. This is known as a many-to-one function. All right, and when we talked about many-to-one, we're talking about there is more than one. These x coordinates right here, 3 goes to 5, and negative 3 has a y coordinate of 5. All right, that's okay. It's still a function. But it's not a one-to-one function, because when I reverse these, okay, or excuse me, it's not a one-to-one because these two x values are different, but they get mapped to the same y value. So we call that a many-to-one. Well, if you switch the x and y coordinates of a many-to-one function, you get something that's not even a function, because now 5 would go to 2 different y values, which violates the rule to even being a function. So that's why a many-to-one function will not have an inverse. Okay, now if I took that parabola and instead of graphing the whole thing, I restricted the denominator. I said, just take this parabola, but only graph the x values that are greater than 0. That's just the right half of the graph. Now what happens is, if we put our pencil through this, it now would be this graph would have a inverse, because now it passes the horizontal line test. So by restricting the domain, we could turn it into something that did have an inverse. All right. Would this graph have an inverse? So if we did the horizontal line test to it, it only ever touches the graph once. So this would have, that last graph would have had an inverse. Okay. Does this function have an inverse? Well, if we do the horizontal line test, we can see it does not have an inverse because it fails the horizontal line test. All right, the pencil crosses the graph more than once. There's no inverse function because there's 3 x values for the same y value. This is a many-to-one function, not a one-to-one function. And this is the reason why. It's many-to-one. These 3 x values have the same y value. And if you did try to reverse or switch the x and y's, you'd have something that's no longer a function. Whoa! Oh, sorry, guys. Didn't tell me we were going into hyperspace. Okay. Pulling a lot of G's right now. All right. So this would not be a... this would not have an inverse. Okay. Usually they kind of warn you when you're going into hyperspace, but they didn't. All right. Should be coming out of it pretty soon. All right, so when we did functions yesterday to graph a inverse, whew, all right, okay, to graph an inverse, you drew the graph, okay. Now, if you think, would this pass the horizontal line test? And the answer is yes. So this would have an inverse, and to graph it, we draw the line y equals x, the identity function, and then we take these points and we switch or swap the x and y coordinates, and that's the same as the graph getting reflected over the line y equals x, and there you have your inverse. And you could see if you folded this over that line, it would land on the red graph, and that would be the inverse. All right, so algebraically, the way that you find the inverse, okay, your first step is you're going to replace f of x with y. Then you're going to change any x's to y's and y's to x's. You swap them. You solve for y, and then you replace the y with the inverse sign. This reads the inverse of function f. All right, so find the inverse of 1/2 plus 6 if it exists, and its domain and range. Okay, we're not doing the domain and range right now, so we don't have to worry about that. All right, so let's take a look at what this would look like. All right, so we can see that this is a one-to-one function. It passes the horizontal line test. So it does have an inverse. All right, so now we just go through the process. Replace f of x. Swap your x and your y's. Okay, solve for y. Multiply both sides by 2. And I would have f of x, the inverse would be 2x minus 12 equals y. And then I'm going to take out that y and plug in. What's that? Hyperspace coming up? Okay, thanks. Thanks for telling me this time. Jeez. All right, so F, and that would be 2x minus 12. All right, now we're going to go to Desmos and graph this. So we type in our original, then we're going to type in y equals x, and then we're going to type in y equals 2x minus 12 and see if they're reflections of each other. All right, and that would look like this. And we can see that these two lines are symmetric with respect to the identity function. We take a point there, like that would be 0, 8, or let's see, that's 2, 4, that's 0, 6. And this is 6, 0. So yeah, those are inverses of each other. Okay, let's take the next one here. Find the inverse if it exists, and we're not going to do the domain and range right now. All right. So does this pass the horizontal line test? Yes. So it's going to have an inverse, right? And now we just go through our steps. Okay, switch our x and y. All right, and now we're going to solve for y. And to take, I want to take the cube root of each side. And I end up with the cube root of x minus 3 equals y. And then I'm going to replace that y with my inverse symbol. Okay, so now we're going to type it in. We'll type in our original, this, and when you put this into Desmos, I don't think it has a cube root, so you would type it in as x minus 3 to the 1/3 power, and that's the same as the cube root. All right, so if we did that, we end up with this graph, and we can see, yep, the blue and the red are symmetric with respect to the line y equals x. So we do have the inverse function. If we picked a couple of points, that's 0, 3. And this is the point 3, 0. And that would be the inverse. All right, let's go to the next one. Okay, now we got a rational function. All right, and this rational function, its domain is x can't equal 5 because that would cause that denominator to be equal to 0, and that's a no-no. All right, but if I look at my graph here, okay, this is a one-to-one function. It would pass the horizontal line test. So it does have a inverse. All right, so we got, let's see, now we just go through our process here. Okay, switch our x's and y's. All right, now to solve this, I'm going to multiply both sides by this denominator so I don't have a fraction anymore. And I would, over here on the left, I would have xy minus 5x equals 2y plus 9. Now I want to get y's on one side, x's on the other. So I'm going to move my 2y over. Okay, xy minus 5x minus 2y equals 9. Okay, now I'm going to move my 5x over, and I'll have y's on one side. Okay, put it right over here, guys. So I'd have xy minus 2y equals 9 plus 5x, or 5x plus 9, same thing. Okay, now to isolate y, I'm going to factor out a y here. And I end up with x minus 2 equals 5x plus 9. And then divide by x minus 2. Those cancel. So after all that work, I'll end up with y equals 5x plus 9 over x minus 2. And then our last step is we replace the y with the inverse symbol. And now we verify that. We type that into Desmos. Okay, so this was our original in red. This was the inverse in blue, and the identity function in green. And we can see that they're symmetric. If you're not sure, just pick a point. Okay, that's the point. Let's see, -2, 0. So the point 0, -2 should be on the inverse, and it is. Okay, now here's the one where if this was a full parabola, it would not have an inverse. But we restricted the domain, so we only have half of the parabola showing. So now it would pass the horizontal line test. And we can find its inverse. Okay, so y equals x squared minus 6 add 6 to both sides. And now I'm going to take the square root. And there's my inverse. Okay, so now when we verify that, we graph it. So the blue graph is our inverse. And we can see like this point would be -6, 0. And here it's 0, -6. So we've confirmed that, yeah, we do have the right equation for the inverse. All right, folks, that takes care of it. The assignment that goes along with this is Math Excel 10. Find the inverse of a function. And I'll see you next time. Take care.